I want to look at the binomial raised to a bunch of different exponents and see if we can't look and see some patterns that develop and that will allow us to expand some binomials to higher powers without actually having to do the multiplication. So over here I have some problems that we already know the answer to. X plus y to the 0 power, by definition, is just the number 1. X plus y to the first power, also by definition, is just x plus y. Now, x plus y to the second power, we multiply x plus y times x plus y. You know, we get x squared plus 2xy plus y squared. And then x plus y to the third, if we multiplied x plus y times x plus y times x plus y, we would end up with this. X cubed, 3x squared y, 3xy squared y cubed. And then the same thing if I took x plus y to the fourth power. For instance, if I multiplied this times itself, I would end up with this right here. So what I'd like to do is to be able to fill in this last row right here without having to actually do any multiplication. So what I need to do is recognize some patterns that I see up here among the exponents and the terms here. So first of all, I know that the first term is going to be x to the fifth power, because when it's x plus y to the fourth, I get x to the fourth for the first term. X plus y cubed, I get x cubed, so on and so forth. How about the last term? To the first power, second power, third power, fourth power, I'm just going to guess here that x plus y to the fifth, I'm going to end up with a last term of plus y to the fifth power. Now, how about the exponents on x? Here I have x to the fourth, now I have x to the third, x to the second, x to the first power, and then over here x to the 0 power. Let's look at the exponents on y. I can think of this as y to the 0 because that's just 1, y to the 1, y to the 2, y to the 3, y to the 4th. So it looks like whatever exponent I start with on the variable, it decreases from that exponent down to an exponent of 0, and the other variable will start with an exponent of 0 and then increase by 1 up to x to whatever power is right here. So I'm going to say that my second term should involve x to the 4th, y to the 1. The next term will be x to the third, y squared. The next term will be x squared, y cubed. And the term after that should be x, y to the fourth. So there I go, x to the fifth, x to the fourth, x to the third, second, x to the first, x to the 0. Y to the 0, y to the 1, y to the 2, to the third, to the fourth, to the fifth. Now, what about the coefficients here? Well, I know my first coefficient and my last coefficient are 1s. What about the coefficient that goes here, 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 and here? I'm just going to show you what they are. This is going to be plus 5 x to the fourth y, plus 10 x cubed y squared, plus another 10 x squared y cubed, plus 5 x to the fourth y, plus 1 y to the fifth. Now, I'm going to go to another board and show you how I know what those coefficients are going to be, and you'll see it's a very attractive looking relationship that I can write by just taking away all the variables right here and just looking at all the coefficients. You just have to realize that the coefficients in front of these terms are all 1s, all the way on down. And then I can just take away all the variables, look at the coefficients, and see if I can see a pattern that develops. So these are called binomial expansions. They're just something to do to recognize patterns to keep you from having to actually do the multiplication to multiply these out. Let's go to the next board. So here is all the coefficients that I had in that nice triangle without any of the variables showing. And if you look at the pattern that's right here, after a while you'll be able to see how you could fill in this next row right here. I'll just tell you that the first number is a 1. Let you think about this for a minute. What's going to be the next number? 6. The next number, 15. The number after that, 20. Then back to 15, 6, and 1. So once you see the relationship right here, you'll know how it was that I could fill in those coefficients in that row. You simply add the two numbers above to get the next number down here. So 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. Down here it always starts with a 1. 1 plus 5 is 6. 5 plus 10, 15. 10 plus 10 is 20. This is known as Pascal's triangle. Pascal was a French mathematician and philosopher, and this pattern of numbers right here is named after him and called Pascal's triangle. Now let me move over here and zoom in on this. I want to show you something else. Here is Pascal's triangle in Japanese from the year 1781. And what's interesting is that if you know that this is Pascal's triangle, you can read these numbers in Japanese. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, that number must be 6, 4, 1, 1, 5, 10, 10, 5, 1, so on and so forth. So if you know Pascal's triangle, you can actually read this number system in Japanese. Now I have one more thing that I want to show you, and that's a connection between Pascal's triangle and the Fibonacci sequence. Let's go to one more board. Okay, so here I've written up Pascal's triangle. I'm just going to rewrite it again, but I'm going to move everything over kind of flush left like this, so the triangle will look this way. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and then finally 1, 5, 10, 10, 5, 1. Now what I want to do is add up these diagonals, up the diagonals on Pascal's triangle written this way, and what you're going to see is the Fibonacci sequence just falls right out. So I'll go up this way, I get 1, up here I get another 1, 1 plus 1 is 2, and then 1 plus 2 is 3, 1 plus 3 is 4, and 1 is 5, and then 1 plus 4 is 5, and 3 is 8. If I was to go down another row here and then add up again, the next number would be 13, because you can see this pattern is the Fibonacci sequence. 1, 1, 2, 3, 5, 8. Next will be 13. So this is something I've always liked about mathematics, when I see two things that initially seem completely unrelated, and then later on I find out that they are actually related very closely with mathematics. So in this case, this is one of my favorites, the relationship between Pascal's triangle and the Fibonacci sequence.